Okay, welcome everybody, and it's a great pleasure to have Partha here. Uh, Partha was also the person who taught me part of complexity 2 and algebra computation when I was a student at CMI. So at that point, he was a PhD student at IMC, and then he drove across the Kelambakam Tambaram character and he has joined Chennai Mathematical Institute. So Partha works in the general area of algebraic complexity, but I must say that he and his collaborators and so on have been proving a series of fantastic results in the sub area of non-commutative algebraic complexity, and which are turning out to be rather foundational for various questions related to this field. And today is going to be one of these talks where you sort of trade off one resource to the other, which I would not have imagined you could do. So this is going to be about trading determinism for non-commutativity in what's called singularity test. Yeah.
Thanks, Ramakrishna, for the introduction, and thanks for inviting me here. So this is a joint talk with Arvind and Abhranil Chatterjee. As Ramakrishna says, that trading determinism for non-commutativity looks up, and I need to explain what I mean by that, but nevertheless. So let me start with this classic problem of posed by Edmonds in 1967. Edmonds was interested to study matching theory, matroids, and certain things. And he asked these very simple questions. You have a set of variables, x1 to xn, nothing non-commutativity. It is commutative variable, normal commutative variable, and you have some field, and you have just given a linear matrix T, which is A0, and every other matrices you scale up by the variable x, you add. So if you look at the matrix T, it's very easy to see that the entries of T are just linear forms over these variables x1 to x. F linear forms over the variable x1 to xn. And Edmonds' problem was, can you efficiently check whether this matrix T is inverted? It's a very simple question. Now, one important thing is that when you address such a question, whether a matrix is invertible or not, you must have a field, underlying field to consider. Then only this kind of question makes sense. Here, the field is very easy to understand. You have these variables, and you have the standard polynomial rings over the variables, and you just consider the field of fraction of that you can easily define. So you have to consider the singularity of this problem over that. That's the problem of Edmonds. Later, I think Lohan also studied a lot about this particular problem. And it is well known that this problem is very easy to solve in randomized polynomial time. You have to just randomly substitute these variables and compute the rank. And this is, in other words, we can use Schwarzschild lemma to argue such things. And what is amazing is that there is no deterministic efficient algorithm known for this problem. And there are enough reasons that Kamenetz and Impagliazzo explained in 2004. If you come up with some deterministic algorithm, then you make a breakthrough. You prove circuit law terms. So we don't expect, we cannot say, but at the moment we don't expect such a result to happen. I mean, it will be a really remarkable breakthrough if you come up with a deterministic algorithm. Okay, so I must say that currently not much is known about this problem. Very little is known from the perspective of deterministic algorithm. So if you even solve some very non-trivial special case of this problem in deterministic polytime, I think people will like it. So very little is known of this problem, and very few subcases are solved. Okay. Feel free to stop me if you have any question. Now I'm moving to the non-commutative version of this problem. This n refers to non-commutative. When I put n in front of singular, it simply means non-commutative. Problem is very similarly phrased. You have a set of variables x1 to xn, but these variables do not commute. That means if you multiply xi with xj, then use this side over here. They are not same as Xj or in the language of this commutator is nonsense.
Also, finite number of variables, like
Finite number.
like constant number of variables is doable for.
Which for this problem? Yeah, even non-constant number of variable is doable in polynomial time. This problem is in P. I'm just coming to
No, not in singular.
yeah, that you can solve.
Yeah. But so what's the difference?
Oh, yeah. So, yeah. So these variables are non-commuting.
Yeah.
And the question I ask is the same. I will give you a matrix whose entries are. I'll give you again a matrix T whose entries will be linear forms over x1 to x. And I ask you the same question: is it singular? Or more generally, can you compute the rank? But here is the catch. Now I am talking about non-commutative variables. So I must first tell you what is the field you are working with, right? And so over these variables, you can talk about non-commutative polynomial rings. So just like the commutative case, this is also ring of polynomials, but they are non-commutative polynomials. In particular, x1, x2 minus x2, x1 lives in this ring as a non-zero polynomial. This is right. Now, this is a ring, and to talk about the rank problem, you have to consider a field of fraction for this ring. And it turns out that although for the commutative case, if you have a domain, you can easily construct the field of fraction just by taking the ratio. These questions are highly non-trivial when you change the domain, in particular when you go to the non-commutative. And fortunately, such a ring, such a field of fraction is constructed long time ago, around 1956 by Amisu. And a good exposition is given in this classic book of Cole and also the book by Noel. So, for this talk, it is not extremely important to know what that field is, but it's enough to know that such field of fraction exists, and you can talk about rank and singularity for this problem. So I just mark that this lives in that non-commutative field of fraction. Yeah, it took me some time to generate the symbol in the LaTeX to actually write it. And the first time I wrote it, my printer was not printing it properly. It always used to print some values. Then we had to fix.
Printer only does commutative.
Looks like, yeah. Okay. Okay, so here the example that I picked up from Vishnu's is that commutative rank and non-commutative rank can be different. So this is a matrix. If you think about this x1, x2 as commutative variable, and you just simply do row column operation, you can easily check that the commutative rank of this matrix is 2. But if you think these variables as non-commutative, you can prove that the non-commutative rank of this matrix is 3. Basically, using elementary operation, you can convert this matrix in this following shape. When this x2, x1 is the commutative. So if it is commutative, this entry will be 0, then you have a rank 2 matrix. Otherwise, it will be full rank, so rank 3. So there could be difference between commutative rank and non-commutative rank. And you can guess that which is the smaller row. Commutative will be smaller, and you can prove that the non-commutative rank is bounded by at most twice of the commutative. Twice of the commutative. Okay, so now the question makes sense. I give you a matrix T, you know that such a field exists, and your task is to compute the rank, or at least to tell me whether the matrix is inverted. Amazingly, in contrast with the singular problem, which you do not know that it is in P, this problem is in P, this n singular. And there are two independent breakthrough results followed by another result. First one by Garg-Gurvits-Oliveira-Wigderson. Second one, this is very analytic. Second one is by Ivanyos-Qiao-Subrahmanyam, and third one by Hamada and Hidden. And the methods are very different. As I said, the first one uses something called operator scaling. It's a very analytic technique, and it works over, let's say, rationals. The second one is extremely algebraic. Okay, I should say that the second one, morally, at least very informally, it is that augmented path algorithm for bipartite matching. It's an operator theoretic generalization of that in a very high level way. Like I like to think of it like that. And this long sequence is sort of like a operator theoretic generalization of augmenting path. And this algorithm works over Q as well as in finite fields. And this third algorithm is totally different. It uses convex optimization over CAD zero spaces. These are not easy convex optimization programs. These are extremely difficult spaces to work on. Okay, so let me remark a few things about this algorithm. They are highly non-trivial analysis, extremely sequential. You would love to have parallel algorithms for this problem, but these algorithms are extremely sequential. And ultimately, you are doing some kind of algebraic computation, and it seems to be using a very different techniques. So apparently, this algorithm does not show any connection to the traditional PIT methods. Like you don't see any polynomial identity testing as such in this solutions.
I mean, usually in the commutative world, a matrix being singular means that there is some rank decomposition that you can.
That works here also.
Okay, and do they also output such a decomposition?
This algorithm doesn't do that directly, but you can modify this IQS algorithm to get the ranking. Okay. And this algorithm is totally different. This convex optimization system. In fact, this is a deadly space to work on, CAD zero space. Okay, so okay, if I get time later, I will tell you probably something more. Why these questions are very interesting from the context of bipartite matching also. Using a characterization called strong subspace, which is essentially the algebraic analog of Hall's conditions for bipartite matching. But let me not go into that now. So when we started examining these three algorithms, what we felt is that can I give a algorithm which is closer to our heart? It uses PIT and some known stuff instead of such a delicate things. And this was the primary motivation to look at this area again. And what we could design a relatively simpler algorithm for this problem, NC. And the simpler algorithm uses strong PIT connection with non-commutative algebraic branching program. Sorry, I forgot to mention what is an algebraic branching program. So
the red button there will move the board up.
So when I say algebraic branching program, the picture you should have in mind is a directed acyclic graph, and it's a layered graph. So you are having edges between successive layers, and these edges are labeled with the linear forms. So if you look at this source and this is sink, and following each path and adding over all of them, you compute a polynomial using source to sink. This kind of objects are called algebraic branching program. So we use that in this PID connection. And more interestingly, this idea of the new algorithm, in fact, extend to this model of partially commutative case and give solution of one of the important problems in automaton. So what I will do, I will first try to describe you some idea of this new algorithm. And then if time permits, I will tell you how this new algorithms gives you the solution to the partially commutative problem in automatic.
So what is this LGP thing is a different paper?
Yeah, so this is the famous paper of Penner, and Keros, where they give a quasi-NC algorithm for bipartite. Yeah, I will tell you why I mentioned it later.
I mean, did you say that you are going to use ideas from that?
No. But this actually motivates you to study this n singular problem. One of the big open problems I get. Okay, so now I'm coming to your point. Like whenever you have a field, any field, the matrix rank is usually defined. That matrix P you can factor like P times Q, where P is, suppose that P is a S cross S matrix, and you have to find the minimum R such that you can factor P which is S cross R and Q R cross S, that R is the rank. Over any field, this definition makes sense. And one of the reasons that this n singular algorithm works in P, because people could come up with a different notion of rank, that turns to be really useful. It's apart from the factorization notion, which is classic. If you take any book, you get this notion for any field, but they come up with another notion of rank and prove these two notions are equivalent. So the second notion that they came up with, that's called block spaces. Okay. So that will play a special role in our algorithm also. So what are block spaces?
So the non-commutative rank, that seems to be the same as. So are you saying that that's the definition? Right?
That's the definition.
But so that's like the same notion as
Commutative rank. But because of this another characterization of that rank, it is easy to compute it. That characterization I'm going to define. This definition makes sense over any field. Whenever you have a field, you can have this definition. Okay. So given this linear matrix T and a matrix tuple P1 to Pn in some D dimension, you can evaluate that matrix T on that tuple. So how do you evaluate? This xi you replace by pi and you take tensor with ai, and a0 you just take tensor with the suitable identity of the same dimension. So that way you can define this space Tg. It is nothing but it's all evaluation of the matrix T over all possible such n tuple of d-dimensional matrices. You take a tuple, evaluate the linear matrix, you get another matrix. You collect all of them, that is called as space T. The definition is clear. And rank of the space is the maximum rank of these matrices. Now notice that when I substitute these variables by pi, you are just operating with scalar matrices. There is no longer variables surviving. You are normal matrices and you talk about the normal rank. So the rank of the space is the maximum over all P rank of this matrix T.
P1 to, sorry, I just missed something. So P1 to Pn, that's a vector of normal scalars.
No, the vector of matrices.
Oh, vector.
There are d-dimensional
It's
matrices.
because you want a non-commutative.
Non-commutative.
Yeah, so it's so each of this. Oh, I see. Okay.
But is D like D has to be chosen?
D has to be chosen. In fact, in the that's a good point. In the algorithm, they will search for such matrices, and your D also should be polynomially bounded. At the moment, it's just a definition.
So if D equal to 1, this is the standard commutative rank.
Sorry, say.
For D equal to 1,
It's a standard commutative.
commutative rank.
No, but how large should D be is not clear.
At the moment, not clear,
Yeah.
but you will see that D will be eventually polynomially bounded
In N.
in the dimension of the matrix S.
That would be a theorem.
That would be it. That's not Agawak theorem. That's already proved by this one. Okay. So I said that these two different notions of rank are connected. So for that, the very nice thing about these block spaces is that the maximum rank in this space is always a multiple of T. That seems to be that's a non-trivial statement. That's not a easy thing to prove. Why should it be multiple of T? But this is something that they have proved, and today it is known as regularity. And in particular, the non-commutative rank of the linear matrix T will be defined by this this rank of this space divided by D as D goes to infinity.
Sorry, a very dumb question. So as D increases, is it obvious that that quantity rank
It's kind of monotony.
is a monotone?
This is not obvious. This was proved.
So you will learn.
They are called weakly monotone. It will not fall again as D.
Right.
Why can't we just, I mean, you can invert
Just zero out.
zero of the.
Okay, zero.
Sorry?
So it's just zero out the last row and
No,
column.
this is a maximum.
Yes, but the maximum includes all of these things, so it's at least as large as the previous one. So if I'm looking at D plus one, I like all the D dimensional matrices are embedded inside the D plus one dimensional matrix. So
Okay,
the maximum and
say,
D plus
like this is the initial.
so the rank D plus one is the
Yeah, maybe if you just want to say that it is increasing, maybe it is increasing.
Oh, but the ratio need not.
Yeah,
be-
the ratio. Yeah. Like without the by D, it would have been immediate.
Yeah.
Without the by
But you
D.
have to divide it. You cannot,
Yeah.
when you cut off some part, you cannot
Yeah,
divide by D minus 1.
Yeah.
You have to still
Yeah.
divide by D. And in fact, this is one of their theorem by Duxen and Macau, that this inner rank, that usual rank of the matrix, is equal to the block. Yeah, I think the division will be the problem. You can just use standard rank. Okay,
So
so
here inner rank was the first notion of rank.
the standard notion of rank, that is factorization. Now, this gives this concept of witness. If you take a matrix tuple, I will call it witness of rank at least R. If rank after you substitute variables by these points is at least R times T, then I will call such a tuple as of rank R witness. Any questions so far? The definitions? In fact, the exact statement of the regularity, or I would like to call it as rounding lemma, is the following. If for some matrix tuple P, you could see that rank is more than R times T, strictly more than R times D, then you can find another tuple that will round rank to the next integer. That means you can find another tuple Q such that the rank will be more than equal to R plus 1 into D. So from R you do a rounding and go to the next integer R plus 1. And how to prove such a lemma is not, it's not very difficult, but you need some concepts from finite dimensional division algebra to prove such results. I will later show you one slide what these objects are. These are classical objects. You can find them even in the textbook. For example, this book by Lamb has a good overview of these objects.
So isn't this just a corollary of the fact that the rank has to be a multiple of D?
Yeah, so that is also not easy.
Okay.
That also.
So you're saying that this statement is equivalent to
That statement, yeah. And proving the statement requires the object.
Okay.
Now, with this background details, let me go to our algorithm. What is the algorithm?
So this is an algorithm for
N single. This is an alternative algorithm for n singular that actually sets the stage for the later results.
The previous theorem you had, that's an, oh, so the lemma is an algorithm statement.
So this lemma is not our lemma. This is by IQS or Dux lemma. So we use all these lemmas and make our PIT connection to give you a new algorithm for n singular.
No, but, I mean, like, basically, Mridhan's question. I mean, like, for example, suppose you have you're given a witness P that says that the rank is at least R, and it's strictly greater than R. From P, can you construct a Q? So, does the lemma actually give you an algorithmic process to get Q from P?
That's what
This lemma, yeah.
Okay.
It is a constructive.
Oh, sorry, sir, I missed the polynomial. Oh, okay. So you can output a Q such that. Oh, I see. Okay. Okay.
And I suppose that there are lemmas which talk about existence of a polytime algorithm without giving one, but this may not be.
It is constructive.
This
This lemma is constructive.
The graph minus here.
I think once you see the state of the algorithm, it will be more clear. So here is the algorithm. So this is the input matrix key, and your goal is to compute the rank of this NC rank of this matrix key. And what is the natural intuition? How do you go about proving such a algorithm? I mean, the obvious strategy will be you have some witness for some rank, you try to increase it, and then try to round it to go to the next integer. That should be your natural goal. And in fact, we do exactly that. So suppose that you already have a rank R witness in D dimension, and you want to check whether this is the maximum rank that you can achieve. You can see in sense there is a similarity in the matching ideas. If that is the case, you stop it. The algorithm just stops it and output the rank equal to 1. Otherwise, it uses a rank increment step to produce a rank witness of more than 1. But it is just more than 1. Ideally, you would like to have R plus 1 so that you go to the next integer. For that, you use the rounding using division algebra to produce the witness of rank R plus 1. And it turns out that if you don't control the dimensions at every stage of your algorithm, the final dimension will be too big. So somehow you have to also cut down the dimension of the matrices that you are using.
Sorry, where is the dimension increasing here?
No, this process will repeat many times because the input matrix is of size S. So potentially rank can be S.
So in step 3 for like
So
step
when you repeat this whole process,
oh,
then the dimension could increase.
So does the rounding lemma increase?
no, the rounding lemma kept dimension
See,
the same.
this is this entire process I am repeating. So this is only for one step of rank increment, then I will again try to increment the rank.
No, I agree, but I'm saying among steps 1, 2, 3, and 4, suppose you start off with a witness of dimension D, which of these steps will increase the dimension?
So this step will not increase the dimension, but if you allow the D, the next time when you come back, that D will be some other function, it will be growing function. So this entire thing will repeat like S times.
No, but when you go from R to R plus 1, so P you started was in D dimension, right? Every all the n matrices were D cross P. Now, when you say that the rank is greater than R and then you round it up.
This step will increase it. Rank increment.
Okay, that will increase.
There are two things, like here also it will increase, and if you don't, it just neighborly to anything, then entire outer loop will also increase the dimension.
No, but step 3, the rounding lemma does not increase.
No, that will not increase.
Okay.
So this step will increase.
Oh, so step 3 will not increase.
The rounding lemma will not increase. But here I will cut down because you will repeat this step again, that entire loop. So if you don't cut down here, the next time it will grow, next time it will again grow, and finally it will land up in exponential dimension. Okay, so as I said that this rounding and blow-up control is essentially from the older paper that I used. Our main novelty in this new algorithm lies here. This rank increment step is very different. It is not using Ohm sequences. This uses a PID connection. That
How is step one done? How do you check if it's done?
that when you cannot increase the rank increment, there will be a criteria from where you will understand that you have reached the maximum rank. So either you will increase it or you know that point itself.
So this reminds me a little of this PTAS that laser gender.
Yeah. Actually, you are right. Yeah.
Except there was no, I mean, there was no way of going from rank RD plus 1 to R plus 1D, which is between step and like the step 3 here was not there.
There is no rounding in the
there was no.
because that's a commutative.
Right.
So yeah, some let me give you some proof idea. So given such a matrix, linear matrix T, in our algorithm, what we will do, we will fix this Z1 to Zn. They are D cross D generic matrices with non-commutative variables. And from T, you will define this matrix over Z variables that I call TDZ. It is just by changing this variable xi by this matrices zi and tensoring with an. Why we do such a thing? Because what we could observe is that NC rank of this new matrix TD, it just defold of the NC rank of the original matrix T. And it turns out that it is somewhat easier to work with this matrix TD than the original matrix T. You can also expect it to happen, like you just blown up everything by a d-dimensional matrix. So there is no big surprise that the NC rank will be changed by a factor. This is really technically easy to work with and reduce this problem to the PID problem. And this is the connection that Mrinal was mentioning, like connection like the Blizzard script. So now, if you look at this TD matrix and shift by matrix tuple P1 to Pn, which was witnessing of the fact that rank R. This will be linear matrix over Z variables. And using some row column operation, you can give this matrix to a special shape. This is IRD minus L. L is some linear matrix, and this is C minus B IRD minus L inverse A. Now, coming back to Rinal's question, if you see that this place is a 0, then you know that you cannot increase rank further. Then you have already saturated the rank.
So what is so IRD is just the identity of
dimension.
What is L?
L is some linear matrix.
So it's so these are so L involves the Z variables.
L involves Z variables. After this U and V operation, you can write this matrix in this shape. So if this is 0, then you can easily check that you cannot increase rank further. And you have already got a rank witness R, which is the maximum possible rank that you can increase.
And checking that is some PID instance.
This is a PID instance. So this PID instance solves two parts. It checks whether it is 0. If it is 0, there is nothing else you can do. If it is non-zero, then it finds a way to increase the rank further. Any other question?
I understand to get a. So you have a particular witness P1 through Pn, which achieves certain rank.
Yeah.
So should we think of this as saying that they are trying to somehow perturb the PIs using these generic Z variables and asking, is there a way in which I can now increase the rank for these perturbed PIs? And
it's related to called shifted. The shifted PIs at the moment are same PIs.
yeah. So So the thing is, I mean, like IRD minus L is a matrix that is made up of these Z variables.
Right.
So the inverse is something that lives in the free skew field.
Yeah.
And we want to check if that is zero or not. Like, is there anything that makes it non-zero?
Any substitution. And in fact, U and V are invertible matrices.
Sorry, those BAs, what were those BAs?
They are matrices. B, I, R, T minus L.
No, but those BAs are like matrices
Over Z variables.
over Z variables.
Now X variables are gone. They are replaced by Z variables.
So it's just in that form for some matrix B and some matrix C.
True. And this is the connection that you can easily prove that if NC rank can be increased, then this right diagonal entry must be non-zero. Otherwise, you have already achieved the maximum witness possible.
So here, what are A's and B's? A's and B's also involve the variables.
Yeah, they also involve the variables. Yeah.
I mean, this is just the old matrix probably looks like A, B, B prime, C or something.
True. The old matrix are
And these are the entries that you get after.
Now, if this is non-zero, then there will be some entry where it will be non-zero. Let's say that ij entry will be non-zero. That ij entry I call Pij. So this is like ith column, ith row of this matrix B and the jth column of the matrix A. And here happens. So that means this infinite series has to be non-zero. Okay. Now, we just use a standard technique.
What is the infinite series?
This is the infinite series. It's Cij minus Bi, IRD minus.
Oh, the inverse. Okay,
Because of the inverse, it's a infinite series. You can expand it like I plus L plus L square L cube. That
I mean, that still works in the non-commutative.
Yeah, that's still works.
So because there's only one end.
okay, it's only one. And now what we will do, we'll truncate this infinite series to up to finite point, and that will be a polynomial. And in fact, that will be a branching program. So
but it was not a formal identity. It's just nothing numerical. So L is
yeah, it's a
No, it's just a
Formal
element with itself, so it's okay.
no, that's fine. But it works. Like your number that only works. L has operator now.
here that is not the case.
Here it's not.
It's
Okay.
just a symbolic manipulation. So, and it's a classical result by Surzel-Berger. It's good reference in this textbook by Eilenbart, that this series is non-zero if and only this truncated series, which is really a polynomial. If you truncate the degree to be at most R into D, that will be non-zero.
This result is about non-commuting variables.
Which is
This Schulzenberger's.
yeah, originally they proved for the non-commuting variables. They proved it in the language of weighted automata, but for us, it's enough to think in this language.
Because we don't know similar statements of commuting variables.
And this proof is very elementary. One side is immediate. If it is zero, then it will be zero. But other side, it's a simple linear algebraic argument that if this is non-zero, the first non-zero term cannot come for a very far distance. You must have something at the beginning. So you can easily prove this linear algebraic statement. And in particular, notice that this has a small non-commutative branching program. Just think of it as a small branching program. And this is the PIT connection.
And the non-commutativity is helpful because this B, like, as the degree increases, these terms cannot cancel each other.
Non-commutative is that we start with the non-commutative set of variables.
But the result is probably for commutative, right? And is that because
Oh, this commutative there is no such difference.
yeah, so it fails. So the reason so as so it helps because for different K, you
If you're going to see cancellation, they have to start happening.
See, different K.
If you take two different paths, one takes the first variable X, the second takes
Yeah, it cannot be.
they will never cancel.
or even the path length matter.
Yeah.
So different K, which is anyway different homogeneous component.
Yes,
So
in
it is
the non-commutative world, it's harder to arrange for cancellations.
Yeah, and in particular, you cannot cancel across degrees because they're just different degrees.
Yeah,
But that you can't do even in the commutative.
Yeah, that is even in the commutative you cannot do that. What is
But in the
difference is that you have this prefix property that something upfront will be nonce.
Like if you see a monomial Z1, Z2, Z3, it has to come from choosing Z1 from the first matrix, Z2 from the second matrix.
It fixes
So it fixes the order in which.
That makes the identity testing possible.
Yeah.
In commutative, such a statement you cannot even test, but in non-commutative you can test, and that is the next.
No, but the fact that, you know, you will see a zero within the first so many things. Does that even the statement says for commutative variables? I thought that statement was for commutative as well. I mean, the testing might fail, but the existence of a finite I given by the upper bound, that's just a linear algebra.
That's just linear.
That does not
involve any non-commutative.
non-commutative. Yeah.
In fact, I can show you the
I mean,
statement.
you could have something that looks like 1 minus x into 1 plus x squared, blah, 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 blah. And it's not like you see a non-zero soon, right?
Say
In the commutative world, because I mean this is like it's like a power series that you sort of have.
Yeah, I think what is 1 minus x into 1 plus the x plus x square. That is just 1. Like
the way I see it is the following.
1 minus x into 1. Or 1 minus x times 1 plus x plus x square. But I just put in the non-commutative.
The one being there is helpful.
Okay, I'll come back to this point.
It doesn't work, but it's the same in commutative.
I think that should go from everything.
So, are you thinking like it's? I think the lemma that I discussed with you here. There is also a notion of the words going on. Like I want to identify the minimal word that is surviving, and there the commutative and non-commutative makes a difference.
Right.
The point to phrase it like that. What is the minimum length word that is surviving in the series? The point is that the minimum word length word that is surviving in the series will be within s plus 1, let's say. It cannot be the case that the first s plus 2 length word is a surviving word.
And there you require.
There I will use the non-commutativity property.
This is probably like a path in a graph with some word like a certain number.
Yeah, because
we only that we.
You can define this concept of the prefix
Yeah.
for the non-commutative word. You know that if I write you word xi1, xi2 up to xin, I have a notion of the prefix, and there the non-commutativity will help. I'll come back to this thing. Okay, so the next step is that I use we use a very standard PIT algorithm to come up with a non-zero of such non-commutative polynomial, and that I call it Q bar, and that Q bar serves as a witness which is more than 1. So to summarize, you have 3 steps: the rank increment, and from this R you go to R plus 1, that is the constructive regularity lemma, and then you have blow up control. You bring down, here is a place where you will incur some dimension increase. You will do some tensor operation and that will change your dimension. You have to cut down it and you repeat the. I skipped many details, but this is the rough sketch.
So this dimension reduction, does it come at any cost?
It's a polynomial term, not polynomial term. It's a polynomial. Okay, so summary so far is that the rank increment stake is a new contribution. Yeah. And the cyclic division algebra object that we use in this construction is the following. If you are familiar with these objects, it's not very difficult. You have this Q and okay, so let me just see. Okay. So now let's come back to the main point of this talk. So this is the trade-off results. Now you have a set of variables x1 to xk, where every xi's are non-commuting variables, but across, so these are I call the buckets, and across two buckets they commute. So that's I call like a partially commutative model. And your problem is the same. Given a linear matrix over such a variable set, can you check whether T is invertible? Now here you have a problem already, like this ring of polynomials are defined over x2 to xk. But what is the field of fraction for such a ring? Is it obvious? It turns out that in the non-commutative setting, even if you are working with a domain, the constructing of field of fraction is a non-trivial task, and it is not very immediate. When a ring will have a field of fraction. And it turns out only 2020 such a construction people have made. Like for this ring, these three mathematicians, Plains, Vinnikov and Walton, they constructed a field of fraction on top of that ring. And this is very useful for us because without this field we could not have done anything. Even the question does not make sense. The singularity problem.
So why can't we just take the same old free skew field and just add those relations?
No, you can't. You have to prove that this multiplicative structure is a group. And it's not easy. I mean, they do such thing, but the proof is not trivial. It's not immediate. The proof. In fact, I can give you.
It's just that I don't know what I'm supposed to prove.
Yeah. In fact, I give you an example of a domain which does not have any field of fraction. It is not embeddable in any field of fraction, which is never the case in commutative.
So what is such a domain?
Yeah, it's not easy to describe, but but this is a non-trivial problem, like finding a field of fraction for a non-commutative ring. It's not an easy. But we only need that such a field exists. We don't need to work inside that field.
So it's not. So is it a construction problem, or it's showing that it's consistent? I mean, like
It's a construction. So this paper is a construction.
in the sense that all the fractions have to be there, and so the problem is, I mean, in the sense that for everything not the ring, for everything in the ring, like for example, if some alpha is in the ring, your field of fraction must contain 1 over alpha.
Yes.
Okay, but it should also contain the inverse of 1 over alpha plus 1 over beta.
Yes, that is true. Yeah. So it will contain all these things.
Oh, and then
So
at
at
the point
it might need
problem
more.
there.
It might need more things than just this.
Yeah.
Unlike the commutative case.
So our main result is that this problem can be solved in polynomial time for k equal to order. And the field we always consider Q, and at the moment it does not work over finite field. The reason is that this construction is not known over finite. This construction at the moment only known over characteristic 0. So if someone can make this construction field independent, our algorithm will be also field independent.
Sorry, does your algorithm need to have any sort of, I don't know, handle on what elements of this field look like, or
not really, but one thing we use from this paper that was possible en route to the construction of the field.
Okay.
At the moment, you can ask what are the witness in the blow-up definition. We had a nice witness concept. Here, what is the witness? that witness, such a witness exists, it comes from their paper. And en route to this problem, actually, this is the main problem that we were interested for a long time. We could solve the well-known problem of polynomial time algorithm for equivalent testing of k-tape weighted automaton. For again, the tape number is constant. Okay, for this talk, I will not define the problem in the language of automata theory. I will give you an algebraic formulation of the problem. But this question has a very long history. It was asked by several people have studied, like from Revin, Scott, Whitfield, Bird, Valiant, Friedman, Harzu, and the result that is very instrumental for us is the result by Warrell, 2013, where he gave a randomized polynomial algorithm for this problem. And the main question also, can we find a deterministic polynomial algorithm? And this is what we settle that. Okay, so here is the algebraic description of the problem, not through automata theory. So you have two linear matrices, T1 and T2, over this set of variables, x1, x2, x3, and you have vectors e1, v1, and e2. And all you want to check whether these two infinite series are same. Just like the earlier one, but here to define the infinite series, you have these partially commuting variables. For example, if you take just two sets, x1 and x2, look at these two words. These two words are actually equivalent because the variables in x1 and x2 are commuting across them. And because of this kind of relation, I think this problem remained difficult for a very long time. People could not prove in polynomial time how much it is the equivalence of these two sets. In fact, the decidability of this problem was not known for a long time, and these are the mathematicians who settled it in 91.
Is there some typo in x2? There will be x2, x2 prime, and x1, x1 prime? No.
No, this is not.
x2 and x2 prime do commute with each other.
Yeah, but then they should be in capital X2, right?
x1 prime and x2 prime, the many
Not commuted, there is a different.
Oh,
Things in the same group. Same.
inside the same group, they do not commute. Across the group, they commute. And Warrell's key insight was to reduce this problem into again a polynomial identity testing for KB. So first, he proves a truncation argument. Like if two infinite series are same, if and only they have to be same up to a finite length, which is for his case it is S. S is the dimension of the matrix. So to prove that, he had to extend that Heisenberg type of argument over a different field. And once you prove that, you can combine these two infinite series into one, and you can come up with one matrix P by diagonally putting T1 and T2 and two vectors U and V. And you can just ask whether this polynomial is zero or not. You can club these two things together and ask the EIT question for one polynomial over this variable set x1 to x2. This is the formulation of the problem. And to solve this, Warrell developed a randomized polynomial time algorithm. This you can think of like a generalization of this well-known Amitsur-Levesky theorem in the noncommutative. And this one, we de-randomize it, this problem in it. This is the main contribution. Yeah, coming back to your point, so there are non-commutative domains which need not to be embeddable in the field of fraction. And there is this classic paper of 1937 by Malsey. he actually constructed one such non-commutative domain which has no field of action. It's an involved paper, invention. Okay, so what are our key algorithmic ideas? Our main algorithm ideas are generating two recursive subroutines. We generate a PIT algorithm for algebraic branching program over these partially commutative variable sets. And we also generate another algorithm that computes rank. And these two algorithms they interact with each other in the build of it. So in particular, what this PCPIT algorithm does, it takes a ABP over this variable set X and it finds a non-zero assignment if the ABP is non-zero. And this PC rank algorithm, what it does, it takes a linear matrix P and it assigns a matrix assignment to the variable which witnesses the rank. And how do they interact? This PC rank algorithm over K buckets will call PCPIT algorithm over K buckets. And in turn, this PCPIT algorithm will recursively call PC rank K minus 1 buckets. So this is the reduction. From K, you go to K minus 1 recursively.
So the matrix assignment that you're going to come up with are going to respect your.
Very good point. The partial commutativity structure. And that is the case you need that paper. That such an assignment in fact exists. Yeah, so as Ramprasad pointed out, so this paper KDB proved that there exist matrices where the ith bucket variable you will substitute by identity on the other coordinates, and on the ith coordinates the non-trivial matrix. And notice that this kind of substitution will respect the partial commutativity structure because they are just tensor over other component. And after the substitution, that T will evaluate to invertible matrix. Or if it is a rankar, it will give you a rankar with this. How much time I have? 5 minutes.
5 minutes.
So in a sense, our algorithm searches for such substitution. And it also constructively proves that, so their paper is not constructive. It's a non-constructive argument that such matrix tuple exists. So our paper proves small upper bound on these dimensions. They prove these dimensions are finite. We prove that these dimensions are very small. If the size of the matrix is S, the dimensions roughly look like S3. It's 100 ways. So as you can guess that we will take the same route. In between, we replace that NC-PIT state by a PIT over this sort of variables. That seems to be the most natural thing to do. But you can ask like why the Rashfield algorithm or well-known NC rank algorithm does not work in this case. The main difficulty is that, as someone I think already from the audience pointed out, for the non-commutative case, this monomial has unique parsing property. If the monomial is x1, x2, x3, the only way it can be generated x1 first, then x2 second, and x3 third. And this unique parsing property is destroyed in this model. And somehow, because of this difficulty, the Rashfield algorithm cannot capture it. And this is the main reason I think the polynomial algorithm was open for this problem for a very long time. So we need a stronger technique to tackle it. Okay, I think if you have not seen Rashfield algorithm, this could be slightly not technical. So in particular, Rashfield algorithm is a very simple linear algebraic algorithm, and it iteratively tries to find a non-zero monomial of the PIT, and it solves standard rank computation. It does. For this problem, we have to do rank computation over a different kind of matrix. For this problem, when you are tackling this PIT problem over K buckets, you will be solving a rank computation problem for matrices whose entries are branching program over K minus 1 variables. So they are not linear matrices. These matrices will be, entries of the matrices will be itself ABPs, and they are over K minus 1 variables, K minus 1 buckets.
So you're basically going to think of the branching program as doing non-commutative computation over say first bucket.
Right.
And then
And pushing other thing into the other field, and then you homogenize it and try to do a Rashpilka, and then you get a matrix of ABPs over these variables. But one needs to be careful, it is no longer a linear matrix. So we find a way to linearize it. We find a linear matrix out of it, whose rank will be sufficient.
And I'm guessing there's some growth in so linearization grows at this dimension.
Linearization is only a polynomial growth.
But it grows the size of the AP or the dimension of the matrix increases in the problem.
Yeah, so it will change the. So here you are solving a rank problem, and this rank, the size of the matrix will increase when you linearize it. But it's a polynomial increase. Yes, there's technical details I don't have time to see. And as you expect, that PC rank algorithm will change this NC rank to this current setting, and we will roughly follow the 3 steps again: rank increment, rank rounding, and blow up control. In a sense, this is only possible because of our PIT based algorithm. The other algorithm of warm sequence and operator scaling, we do not know how to tackle this problem. So here is a quick sketch. So the Z matrix lemma will change to now the tensor shape, and you identify this rank T and the rank of the new matrix, just like we did in the non-commutative case. You again do this translation business. Here you land up a PIT problem over the K buckets that you reduce to a K minus 1 bucket. So the depth of the recursion, you can see that it is at most K. Maybe I will skip this thing. And some final remarks. So runtime seems to be it's a little bad. S power 2 power K log. But this Orell's randomized algorithm is like S power order K. So ideally you would like to have an algorithm that is not W exponential in K, single exponential. We do not know how to do that. For non-constant K, we do not know the complexity of this problem. Even randomized, we do not know how to solve it. No hardness results also. So, yeah, I guess that this PIT connection could be helpful in attacking this black box problem for NC problem, which is open for a very long time.
I mean, so this was a non-black box.
It is purely a white box. Even making this, even before making this algorithm black box, we have to solve that NC in black box. And for that, I feel that PIT connection could be helpful, but it's a long way to go. Maybe I should stop here. Questions?
Okay, if not, let's start Partha target.
Should we want to see that?
Yeah. It's not that one.